competition. So a brief overview of our presentation. So first we'll talk about what is CanSat. We'll talk about who we are, our mission, software, electronics, hardware, the real world application, and high school opportunities. So what is CanSat? CanSat is a competition of high school students run by the European Space Agency. And in the competition, students get to build a small simplified satellite. And the challenge of the competition is to fit all these different systems of the satellite, like the electronics, sensors, computers, all that kind of stuff, all into the space of a soda can. So then your CanSat is then launched by a rocket or dropped by a helicopter at an altitude of 1 kilometer. And then during that descent, you have to conduct all your scientific experiments, achieve a safe landing, and then analyze the data you've collected. So for the competition, you have both a primary and a secondary mission. So your primary mission would be to measure both air temperature and air pressure during the drop. And then if you're an advanced category team, you would transmit this data in real time back to the ground station where you'd be sitting. And then as well, you also have a secondary mission. So the secondary mission can be honestly anything. It's selected by the team and it can take ideas from real satellite missions, collect scientific data for a specific project, make a tech demonstration for something you've designed, or anything. So I know other teams in previous years have made a sort of satellite that has basically a drone inside of it that unfolds and controls the descent of the landing. And as I mentioned before, this competition has 2 categories, advanced and beginner. So for the advanced category, each CanSat transmits the measured data by radio in real time to a receiving antenna on the ground, which each team also has to make. So then for this competition, if you're in the advanced category, your team would actually have to travel to the launch site, which is in Calgary in the spring. And then if you win the advanced category, you get to go on and represent Canada at the European Space Agency and competition where you'd actually go to Europe and compete there. So for the beginner category, we're a beginner category team because it doesn't actually require you to travel to Calgary, which is a bit of a time investment that some teams may not be willing to make. And then for the beginner category, instead you would transmit all your data. Instead of to a ground station, you'd store it in a SD card on board. So you might be asking, how can I participate? So you'd have to be a high school student. So if you're in grade 8 or up to grade 11, you can look forward to participating next year. And it runs every single year and registration starts in September. So it's teams of up to 6 high school students. And it's highly recommended you have a team of a wide variety of backgrounds, both design, coding, and all that kind of stuff, because you need different expertises in order to succeed in this competition. As well, you'll need a teacher supervisor and a secondary mission. So just a teacher supervisor to make sure nothing goes wrong. And your secondary mission, as I said before, is a mission that you decide. And then seen on the presentation right here is the link to the web page where you can sign up, and there should be a link next here to sign up. You can also go on Google and just search Canadian CanSat competition, and there should be a page for it. Then, who are we? So we're a group of students from both Richmond Hill High School and William Lyon Mackenzie Collegiate Institute, or you might know us as MAX. So then we're all grade 12 students, and we're all from a bunch of different backgrounds, and we have all different expertises. So I'm Jerry, I'm the team leader, and if the rest of the team wants to introduce themselves.
Hi.
Jim, do you want to introduce yourself?
Okay, hello. My audio working? I'll assume that's a yes.
I worked on some of the software in the project, mostly just the data analysis from Richmond Hill.
Hello, I'm Quentin. I'm from the Max program at William Lyon Mackenzie, and I worked on the firmware for one of our systems on the satellite.
Yeah, and I'm Suyu. I did some of the design for the 3D printed components and also the Arduino code.
I'm Ben. I did some of the simulator stuff.
All right, so moving on. So our mission, and so as you know, every single team needs to have a secondary mission that the team gets to decide. So our mission is, because we'll be launching satellites in Calgary, we're inspired by all the recent wildfires happening in the area to use a bunch of different sensors and camera systems and whatnot to record images and data in order to analyze and predict wildfire risk. Because we'd use variables such as the color of the plants there, the humidity, the weather conditions, and all that kind of stuff in order to create a simulation program that is able to allow the user to input different parameters in order to simulate a wildfire in the area where we've taken the photo. And this whole simulation allows users to identify vulnerabilities of an area to wildfire, because then you can see how can I improve this area's resistance to wildfires, and then potentially look for solutions, as I said, to mitigate risk. And then here we have the different components. So as you know, a satellite is very complex. It has a bunch of different components, both hardware and software. So first, we'll look at the hardware. So the hardware bit is split up into obviously electronics, where you have your pressure sensors, all your different types of sensors, like humidity, temperature, GPS, in order to conduct our secondary and primary missions. As well, we have a parachute in order to obviously decelerate the satellites to a safe speed. As well, we have the software side, which is the non-physical parts. So for that, we have our data processing. We have to take that data, we take it from the sensors and then process it. And then simulation, where we actually run the simulation, as well as firmware, which is kind of the code that helps the electronics run. And next, software. So Ben, if you'd like to take over.
Yes. So the tech stack, which is the different parts of the software we'll be using to create the simulator and data processing parts are as follows. So for data processing, we're using Python because there's Pillow, which is an image processing library, which allows us to take the image we receive from the satellite and analyze different sections of it. And for the actual simulator, we want to run it in a web page so anyone can kind of go on and see how it works and use it. And so we'll be writing it in JavaScript to run the website, and it'll be rendered and the end user can interact with it using more JavaScript-based tools. First, we have to process the data from the satellite. So we do this by splitting up the image into smaller chunks, and then we can look at the color in every pixel in the image. And by knowing colors, we can sort of find the average color. And using that, we can sort of try and figure out the moisture level based on sort of how not green it is, and the packing ratio, which is basically how dense the material is packed in there. So looking overall. And then by using GPS data that we receive from the satellite, we can sort of get elevation data of that image of the area from an external API, so the internet, and then we interpolate that because so the data we receive is like the image on the left. You see it's pretty low resolution. There's a lot of really blocky, but then using interpolation, we can sort of get a little bit more detail by sort of applying a gradient, sort of blurring the data to get a more smooth transition between sections. So the size of each of these data chunks we can figure out because we know the camera has a field of view of 62.2 degrees by 48.8 degrees. And then using trigonometry, we can figure out the dimensions of each of the chunks if the photo is taken by 1 kilometer up. And so we split the units into 133 by 100 units, the grid into that many units. And then using trigonometry, figure out each unit is about 9.07 meters by 9.07 meters, which is pretty large, but considering how high it's taken up, that is actually pretty decent amount of resolution. This is sort of an example of how the data processing works. So the image we receive is on the left. That's just a sort of sample image that we have from Google Maps. And then we split up into smaller data chunks. As you can see, it sort of looks like the image lost quality. It's because it's been split up into smaller chunks. Like we did basically downsize the image. And then by running the program, we can find what 30% moisture content analysis. We can find out which sections have about 30% moisture. As you can see, they kind of roughly correspond to the less green sections of the image. So each of these data chunks we will use as simulation units in the actual simulation. So using the formula that you can see there, that is able to calculate the rate of spread in feet per minute within a single unit using the factors of moisture rate, packing ratio, and wind direction. And then for the sake of simplicity in our simulation, when a unit is fully on fire, it is then able to spread to other units to start fire in them. And each unit has a set amount of time they can burn for, which you can see in the next slide. This is how the simulation would actually work. So step one would be to check for units within a 1 unit distance, other units on fire. Then we calculate the fire spread rate using the before equation. Then we update how much of the unit is on fire because we know the time between steps and the spread rate within them. And then we update how much stuff you can actually burn for, and we repeat steps 1 to 4 again. So in the first image, we see those 4 units are on fire, and they spread their fire to the other units. And then in the next image, the top left unit has fully burned out, and they can only spread. And then we see that the other units are still burning, and then the units that were on fire before are now burning more through. And then finally, in the last step, we sort of see that all those units that were on fire are now fully on fire and have spread to the units next to them. So the simulation actually just simply doesn't actually render this information. So we need to find a way to take this data and let the user view the data. And that's simply done by displaying it over top in a grid on the original image. Then for user interface, it's a simple user interface. Basically, the user can start and stop the simulation, and they can adjust simulation speed, how many steps will be run. And then they need to define a few variables, which is wind, because it'd be nice if the user could, because different days have different winds. And of course, where the fire actually starts. If it comes from the top, it starts in the center, it comes from the right or left of the image. And then potential features that we may add would be the ability to add fire breaks, which would be lines that fire cannot burn through, basically blocking the fire from spreading to certain areas.
So now we'll go on to the electronics in our satellite system. Jay, next slide. So we elected to have 2 different systems on our satellite, a primary system running a Raspberry Pi and a backup system running an Arduino Nano. This way that if one of these systems somehow goes down during our operations, we have one system that's still running, capable of completing our primary mission. These 2 systems have power supplied from 9-volt batteries, and the voltage is adjusted using a buck converter. So our first system is a Raspberry Pi 02W. A Raspberry Pi is a little computer that looks like this. It runs a Linux operating system, and on it we have a simple Python program that logs all of our sensor data and takes pictures and saves them to our operating system's file system. So we have on our Raspberry Pi some pins along the bottom where you can hook up sensors, as well as a camera port on the side. So we have a GPS module and a compass module for recording location data, a pressure sensor for our primary mission, and the temperature and humidity sensor that's also for our primary mission. We have the camera module, which is used to get pictures for our wildfire simulation. And then we have a clock module that is used for the GPS because GPS requires accurate timekeeping. And then our second system is an Arduino Nano. Like the Raspberry Pi system, this also records data to an SD card. And attached to that is a pressure sensor and a temperature and humidity sensor to conduct our primary mission.
Next, we're gonna show you guys with our 3D model of our satellite. I'm going to start screen sharing. Okay, so this is what our 3D model of our satellite looks like. This was made in a program called Fusion 360, which is a computer-aided design program, which allows you to make 3D like visualizations or models of stuff. So then here's the our main model. If I hide the shell, you can take a look at all the stuff inside. So we have all the electronics, like on the walls of the satellite inside, and then we also have, so we have all the sensors, the Raspberry Pi, the Arduinos over here, and more stuff over here. And we have the buck converter over here and space for 2 9-volt batteries underneath. So we can actually show you guys the actual model. So here. So here's our shell. And then we take off the shell and we have the actual model 3D printed out, and we have some stuff mounted on already. So this is how it will look like.
Vivian?
Okay, now on to real world applications. So our secondary mission is used to simulate fire, which can evidently be used to also help stop fires, right? If we know how fire is going to spread, we can predict its path and then stop it better. And then for high school opportunities, because I'm pretty sure everyone here is probably in either high school or elementary school. So if you're in grade 9, there's actually a lot of grade 10 courses you're able to take, like Introduction to Computer Science, where you just learn the basics of computer science in Ontario at least. And then something you might be able to do at the end of the year is to create a game with Pygame. And then this course builds off into 11 and 12 computer science, which once again depends on your school, but you're still learning computer science, probably fundamentals. There's also 10 computer engineering, which once again does build off onto 11 and 12 computer engineering in most schools. In grade 10, you get to learn about the basics of electricity and computers. And as you progress towards 11 and 12, you should probably end up building robots and similar stuff. Then there's tech design, where you design, prototype, and build projects. I'm pretty sure the grade 11 course ends up building a bridge at the end of the year. And then most schools have a variety of STEM-related clubs. Most schools probably have engineering, computer science, math, physics. Those are pretty standard. And then depending on the school, you might have some other clubs like robotics, 3D modeling, this kind of stuff.
Finally, we just want to say a thank you to the STEAM project, which graciously provided us with some electronics. They're a organization that runs STEAM related, so STEM related classes and camps for kids. So yeah, you can check them out.
All right, so if anyone has any questions about either the presentation, our team, or I guess high school in general, feel free to ask them now. And you can either put them in the chat or feel free to unmute yourself and ask a question. So does anyone have any questions?
Can we receive a copy of the slides?
Sure, I'll quickly post a link to these slides right now. Give me a second. And the link should be in the chat. So feel free to take a look either now or after the presentation, as I'm sure there's, as I said before, there's instructions on there on how to join. There's a link there, and hopefully some of you next year will get to participate in the competition. Are there any other questions? No questions? Anyone? No questions?
I guess what we can also do is we can post a link to our website in the chat. So if you want to look at that, you can also.
Yeah, we also have a website for our team. So on the website, you'll be able to find out both about our satellite, our team. There's going to be a bunch of blog posts. We already have 2 up right now, where you can take a look at the blog posts. The ones right now we have are for just a general overview of the electronics, as well as a more in-depth progress report on our electronics so far. And there will be several more coming up very soon, both about the parachute and hardware. So look forward to seeing that. As well, we'll have there's a gallery page on there as well, where you can take a look at our progress photos and like videos of us laser cutting the parachute for the satellite and stuff like that. As well, there's a resources page where you can find the slides from all our presentations we've done so far. And given a couple months, the simulation will be on there as well. So you can try out the simulation when that is finished. Also, I think it'd be a good thing to do to take this time and just talk about some of the challenges we faced during this competition. So obviously in a competition where you have to design such complex stuff like a satellite, there's a bunch of different aspects that can go wrong. So you might go into the competition thinking, okay, this isn't that hard, it's not that complicated, but it's actually way more in-depth than you might think. So you might think, okay, I know how Arduino works, I know how to design stuff. It should be pretty straightforward. It's a very simple competition. But when you actually start getting into it, it's a lot more deep and there's a lot more stuff to do. So for example, some of the challenges we faced were, earlier we talked about having a real-time clock in order to be able to maintain the time for the GPS to work. So that's something we actually didn't know at the very beginning. So when we were testing the GPS, we couldn't figure out why it wouldn't connect without having first connected to Wi-Fi. So then we figured out, okay, the Raspberry Pi has to first connect to Wi-Fi in order to get the time, and GPS actually needs the time in order to work, because that's just how GPS works. And then whenever we started it up on battery, or in the actual launch, you'd be starting it up on battery away from Wi-Fi that you can't connect to, then you'd have the problem where your GPS just wouldn't work. So in that case, we overcame that by using a real-time clock module, which has a battery in order to be able to constantly 24/7 maintain the time. So then whenever we need the time, we can get it. So that's how our GPS works. And that took us a really long time to figure out. It is quite a frustrating challenge we had to overcome. And we did overcome that eventually. Do any of the other team members have other challenges they faced during this competition? Do you?
And another thing we had to figure out, once we had figured out we needed the real-time clock, it was a challenge to try to squeeze it into our existing design. So if I can show you how the clock will fit in. So there's multiple challenges with this because the clock has to have an accessible battery. And it's also really large, so I had to shuffle a lot of stuff around to make that fit.
One of the overall design challenges throughout this entire competition has been honestly fitting everything in, because it's not like so soda can's way smaller than you think. When you start cramming in all your batteries, which already take up like a third of the space, as well as all your sensors and computers and all the wiring, especially wiring takes a lot of space, that really does create a issue, because you have to figure out how to do all that, like Tetris essentially, where you try to slide all the pieces together in your design in order to make them fit nicely. And because you also have to have the batteries be accessible and have different components in certain locations, you need to figure out how to make that work. And that's quite a big challenge that you have to face, not only in just designing a satellite, but also when you're designing different things in life. So if you do go into engineering, this is also challenges. Like, for example, if you're designing a phone, you have to figure out, okay, how do I maximize the size of the battery while also like giving enough room for all the different components in the phone. So it's a very big challenge present all throughout engineering, just optimization. So are there any other questions in the chat? No, if there's no questions, then that's it. You can reach out to us on our website. Our email should be at the bottom of the website. So you can email us any questions about the competition or this presentation or high school. So feel free to reach out to us through the email on the website. Aside from that, that should be it. So everyone is free to go. So have a good day, everyone.
Thank you.